subgroups of the additive group of integers. All right, let's get to work here. Now we're ready to prove something remarkable, amazing, and beautiful. Watch this. Let's say I have my integers, all right? Let's write that properly, z, and it's a set like this, -1, 0, 2, 1, -3, -2, 3, 4, 5, and so on and so on, positive and negative integers and 0. And I know that z with addition is a group. This is a group. I know that. But what if I take some integers? Take some integers. Can I form a group? Like, for example, a subgroup of z plus. Can I do that? Yeah, it's possible. You can take some integers and form a subgroup of z. Yeah, that's very interesting. And we're going to prove a totally amazing theorem. Any group that you can construct from elements of z under addition will be multiple groups. There are no other kind. Okay, no others are possible. That is totally amazing. I find this theorem to be very surprising. Well, maybe if I think about it more and more, maybe it's kind of obvious. I don't know. But on the surface of it, it's surprising. It's beautiful. Okay, surprising and beautiful. So let's get to work. And let's see how the proof goes. We'll need some tools at first. Let's say, part one, okay, let's say U is a subset of natural positive numbers. Positive numbers. Okay, so for example, I have numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I take some subset. See, this goes on forever and ever. This is n. Natural numbers, and I take some subset of this, call it u is 3, 6, 7, 9. Notice that it has the smallest element. Alright, so that's the first thing that we notice about natural numbers. There's something very special about them. Any subset of natural numbers always has the smallest element. Can I prove this? Probably not. I have to take this as an axiom or a given. I think it's a very reasonable thing to assume. I don't think there's any problem with this. I don't see why it needs to be proved. It's completely intuitive. Any subset of n has the smallest element. Okay, that's the first tool. The next tool we're going to need is how to prove, how to show that two sets, A and B, are equal. This is not that simple because let's say A is a bunch of elements, this is A, and B is also a bunch of elements, and we want to show they're equal. Well, one way we can do it is try to match the elements like that and say this element equals that. This may be hard. Be hard to do or not practical. So that's not really how we do it in mathematics. We have a more clever idea that works most of the time. We prove this. A is a subset of B. So that's the first step. We prove this, and then we prove this, that B is a subset of A. Now, the only way this and this can be both true is, you guessed it, if A is B. So that's a technique. That's a technique that we're going to use to prove that two things are equal. Okay, great. Let's keep going with this. Now, the next point. All right? We're going to show that, we're going to look at the structure of H. Let's say H is a subset of Z, and H is an additive group. All right, so it's a group under the operation plus. Now, a simple case, the trivial case is H is the element 0 with this plus. And yeah, that's a group. You can show that this is a group. No problem. It has all of the axioms or all of the properties of groups is right here. No problem. You can prove that. That's an exercise. Do it. Look at the previous videos and prove that this is a group. Now, in another case here, 4, if H is not just simply the set of 0, but then there exists an A element of H such that A is not 0, right? Now, if A is not 0, then A is either positive or negative. So, okay, by inverse property, since this thing is a group, by the inverse property, H is a group, but the inverse property tells me that if A is in H, then minus A is in H. So A and minus A are both in H. So therefore, H has positive elements. H has positive elements for sure. If this is negative, then this one's positive. If this one's positive, this one negative. Either way, there's positive elements in H, one way or the other. So if H has positive elements, now I can go back to this idea. If H has positive elements, then there's some subset of n in H. Therefore, some subset of natural numbers is in H. Okay, what does that mean? Well, according to this principle here, there must be a smallest element. Therefore, there must be in H a smallest positive element. We call it D. Call it D. This is very interesting. Keep this in mind. Smallest positive element. 0 has to be in H because 0 is identity. And D is the next largest element in H. Okay, because remember, we're talking about integers here. We're not talking about fractions or real numbers or anything like that. There's nothing between 0 and D in H. D is the smallest element because of this. H contains natural numbers because of this. Therefore, H contains the smallest natural number, D. Get it? All right, now if D, let's look at this point, point 5. If D is in H, then D plus D, that's 2D, is in H. Why? Closure. Group property. H is a group. It's closed. Now, if it's closed, then 2D plus D, that's 3D, must also be in H, and so on and so on and so on. Therefore, PD, where P is any integer, must be in H. Element of H. And I know what you're thinking. You're thinking, hey, what if P is negative? Yeah, sure. By inverse, if P is positive, okay, PD is in H, then minus PD has to be in H. Both are in H. So what this means is that DZ is a subset of H. All the elements, all the multiples of D are in H. Let us put a box around this. Very, very important. Okay? Very, very important. And let's continue. All right? The next point, point 6. Let's take some arbitrary element A of H and divide by D. You say, what do you mean by division? This is integers. Well, I mean Euclidean division. All right? Real, honest-to-goodness division. Euclidean division. All right, let's do this. So Euclidean division works like this. Okay? A is some quotient times D plus some remainder. Yes? Great. And there has to be a condition that must be true. The remainder must be less than the divisor, but bigger than or equal to 0. This is the Euclidean condition. If you can't set this up, then the Euclidean division doesn't work. For example, if D is 0, you will find that this is impossible. You should try that at home. It's very interesting. Okay, great. So this is what's going on here. Let's now look at this a little bit more carefully. We know that A is in H. This is an element of H. We know that this is an element of H. Why? Because of this. Any multiple of D is in H. We showed that in point number 5 up here. We showed that already. So these two are in H. Therefore, remainder is in H. So R is equal to A plus minus QD. All right, this is in H. This is in H. Therefore, R is an element of H. Why? By closure. Closure. You remember that H is a group. Never forget it. We assume that H is a group. Therefore, H has all those group properties. Let's never forget that. Great. So if R is in H, well, this condition must be true. This is Euclidean division. And here we get to the most beautiful part of the argument. 0, R, D. But D is the smallest positive element of H. Therefore, R is 0. Think about it. This is beautiful. Beautiful. Very beautiful. Remainder is 0. Therefore, okay, A is equal to QD plus 0. A is QD. Therefore, all elements of H are of the form QD, multiples of D. And therefore, okay, H is a subset of DZ. Okay, we're ready now. Let's put it all together. I have a little spot to do that on my board right here. Let's put it all together. Here, this is true. DZ is a subset of H. We proved that here. And now, H, subset of DZ. Well, looky here. Lo and behold. All right? Two sets are equal if this is true and this is true. Therefore, H equals DZ. That is beautiful. That is absolutely beautiful. If H is an additive group of integers, then it is a group of multiples. There is no other kind. No other kind of additive groups of integers. They all look like this, DZ. And the interesting thing, we can take it up one more step. Take D as 1. And we have 1Z, which is the same as Z. Z itself is this form. It is a group of integers, and it is of the same form, except in this case, D is 1. So all subgroups of Z have the same form. They are multiple groups. I think this is a spectacular theorem. it merits careful study, and it could be your motivating introduction to group theory. It's a great way to use group theory to prove something interesting for your first experience with group theory. Okay, next video, we're going to use this to prove the final theorem about linear combinations. Okay, if you like this, click like on the video, leave a comment, subscribe, and hang on for the next part.